Hello everyone and welcome back. We now live in a world with the data at its heart. The amount of data being produced every day is growing exponentially, and a large amount of this data is in the form of events. Whether it can be updates from sensors, clicks on a website, or even tweets. Applications are bombarded with a never-ending stream of new events. So how can we architect our applications to be more reactive and resilient to these fluctuating loads and better manage our thirst for data? In the next session, explore how Kafka and reactive application architecture can be combined in applications to better handle our modern data needs. It will be presented to you by two stunning women, Grace Jansen and Kate Stanley. Grace is a developer advocate at IBM, working with open liberty and reactive technologies. She has been with IBM since graduating from Exeter University with a degree in biology. Grace enjoys bringing a varied perspective to her projects and using her knowledge of biological systems to simplify complex software patterns and architectures. As a developer advocate, Grace builds POCs, demos, and sample applications, and writes guides and tutorials. She is a regular presenter at international technology conferences and has recently authored a book on reactive systems. Grace also has a keen passion for encouraging more women into STEAM and especially technology careers. As for Kate, she is a software engineer in the IBM Event Streams team based in the UK. Through her work on IBM Event Streams, she has gained experience running Apache Kafka on Kubernetes and running enterprise Kafka applications. In her previous role, she specialized in cloud-native Java applications and microservices architectures. Kate has co-authored an IBM Red Book on Java microservices and has contributed in the open source microservice projects Game On and the open source Kafka operator Streamzy. She enjoys sharing her experiences and has presented at conferences around the world, including the Kafka summits in San Francisco, New York, and London, Javaland in Germany, and G-Focus in Sweden. Both of Kate and Grace has each one of them has her own book. I'll be sharing them in the Joy section on Discord. So I will be sharing the links, and you can check them out and give them your feedback. Kate and Grace, hello, welcome.
Hello, thank you for having us. And thank you for that wonderful introduction. So yes, my name is Grace Jansen. I'm a developer advocate at IBM in the UK, and I'll be presenting today with the ever fabulous Kate Stanley.
Thank you very much. Let me just share the slides. Hopefully you can see the slides all right?
Yep.
Okay, let's get started then. So yes, today we're going to be presenting about reacting to an event-driven world. But before we do any of that, let's get some coffee. We all know that everyone loves to have a quick coffee break. Ironically, neither Grace nor myself actually drink coffee. We would rather have hot chocolate. But nonetheless, there are plenty of coffee demos out there that are written to show people how they can evolve their applications and make better choices when they're building apps. So let's look at one such example. This is our barista example. And the barista example is actually a GitHub project, so you can go and check out all of the code yourself if you want to. It's all there up on GitHub. But in our barista example, we have some coffee lovers that are going to the coffee shop. They make HTTP requests into the coffee shop to place their orders, and then those get forwarded onto a barista. If you run and build this application, then it works okay if you've got a few coffee lovers But as soon as you get a lot of coffee lovers, then you'll find that you get a bottleneck. And the bottleneck is around how quickly the coffee shop can process the orders, but also around the interaction between the coffee shop and the barista. And because it's HTTP, you spend a lot of time waiting. So the coffee lovers want to obviously solve this problem. And for these sorts of applications, often a solution that is proposed is to use something called event-driven architecture. So event-driven architecture is this idea of having an event-driven messaging backbone where you have events or messages that are flowing through the system. So here we have producers and consumers that are publishing events and consuming those events back again. So what happens if we put these in the coffee shop? Well, in the coffee shop demo, we still have HTTP for the coffee lovers to place their orders, because if you're placing an order, you want an immediate feedback to say, has my order been accepted? But then we put this event backbone between the coffee shop and the barista. This allows the coffee shop to place new orders onto the event backbone and then respond to the coffee lovers and allow the coffee lovers to go and sit down. And the coffee shop can then process the next person in the queue. In the background, the barista is able to pick orders off the event backbone as and when they're free to do them, process the coffee order, and then put it up onto the board to say that it's ready. So if we run these two different examples, and both sets of examples are written in code in GitHub, if you run the two, you'll find that when you run with a lot of coffee lovers, the one with the event backbone does work a lot better. And when people are starting to build these kind of applications and looking at what they should have as their event backbone, you'll find that often Kafka gets thrown around a lot. So for those of you who don't know, Kafka is an open source distributed streaming platform. It provides stream history, so it's slightly different from some other messaging systems you might have come across. So you can reread the same message multiple times. It has immutable data, and it's really built to be highly available, highly scalable, and provide very scalable consumption. So you can have a lot of consumers reading all from the same place in Kafka. So we have these great tools like Kafka that are becoming really popular, and examples that show us that moving to a sort of event-driven architecture is a really good idea. But often this can be oversimplified. And when somebody asks this question, is your coffee shop non-blocking and highly responsive? Well, actually they're asking, is your microservice system non-blocking and highly responsive? It's very tempting to answer, well, yes, of course it is. I'm using Kafka. But that's not quite the whole story, is it, Grace?
No. So although Kafka is a fantastic tool when we're looking at trying to create a more event-driven type of architecture, as Kate's been explaining, it doesn't make our microservices or our applications or systems as a whole reactive and highly responsive completely from end to end. What we need to look at for that is reactive systems. So what do I mean by reactive systems? So the concept of reactive systems really stems from something called the Reactive Manifesto. The Reactive Manifesto was a specification that was originally laid out in 2013-14 by a group of software developers who were really looking to sort of summarize the key behaviors and characteristics that we want to see when we're trying to build highly responsive, reactive, non-blocking applications. So it consists of 4 key cornerstones. The underlying characteristic or cornerstone is message-driven. So that sort of links into what we were just talking about with really making it asynchronous at sort of the data layer. Interestingly enough, in the original manifesto, so the Reactive Manifesto 1.0, it was event-driven, which was the key underlying cornerstone, but they switched to message-driven in the Reactive Manifesto 2.0, which was released in 2014. If you want to find out more about why they made that switch between the two, there's a whole article and sort of resources online that you can look at with their reasoning behind that. But where does this fit in with Kafka? So with Kafka, you've got sort of different definitions for the two here. So we've got with messages. So messages we've defined as an item of data sent to a specific location, whereas an event is a signal emitted by a component upon reaching a given state. So it's really that difference between just emitting it and anyone being able to receive that, or sending that information to a specific location or service. But interestingly, you can have this sort of weird mix of both, where you can actually encode an event in a message's payload. So in this sense, you can have sort of a mix of the two. But when it comes to Kafka, it actually doesn't matter. So many people sort of associate Kafka with events, But when you actually look at the Apache Kafka website, events aren't mentioned anywhere. It's actually records that are mentioned. So it mentions, publishing and subscribing to streams of records, storing records in a durable way, and processing streams of records as they occur. So with Apache Kafka, you can use it for event-driven or message-driven. So Kafka can be a fantastic tool for us implementing this behavior of message-driven, detailed in the Reactive manifesto. Now, the next characteristic we're going to look at, we want to go back to our example to find out why we need these other behaviors, because you've already covered message-driven in adding in that event backbone into our system. But there are still things that can go wrong with our system that we haven't yet been able to account for, which the other behaviors in the Reactive manifesto will help with. So in this example, we've only got 3 coffee lovers currently, but there are not only 3 coffee lovers in the world. So what happens when we have a huge influx of coffee lovers to our coffee shop? More coffee lovers means more coffee orders. So now our coffee lovers don't have to wait at the till, but they are putting in more coffee orders, which are being sort of uploaded to our event backbone so that our barista can read from them and see which order's up next. But what we haven't accounted for here, and where our point of potential blocking or failure is the barista. So in this case, we only have one barista making all those coffees, and that barista can only work so fast. So at this point, we're going to be slowed down by that barista because we haven't got multiple baristas working on the coffee. This is where elasticity comes in, which is the next behavior in the Reactive manifesto. Elasticity is all about being able to scale our resources both up and down depending on that fluctuating load to our system. So in the barista example, we'd be able to scale up the number of barista microservices so that we could better deal with that increased load of that increased influx of coffee orders. And this way we could produce a much more sort of reactive and responsive system for our end users by being able to elastically scale those resources. Let's take a look at another issue that we could potentially come into. In this case, we've got a downstream component added to our application. We have this coffee table service. So in this case, this coffee table service is representative of any downstream component really, and that could be a database, an external database, it could be a third-party application, or it could just be another microservice that needs to process that data further down the line in your own application. So in this case, what happens in our application is that the barista, in order to serve up the coffees, has to place them on the serving table, and then the customers can come and collect them. But what happens if the serving table starts to fill up with coffees because our coffee lovers are being a little bit lazy and aren't coming to collect their coffees? Well, in this case, our serving table is now full and our barista is having to juggle coffee because they can't put it down on the table. This is sort of representative of maybe that downstream component going down or being stuck in some kind of process. So in this case, what we need to implement is the behavior of resiliency. So resiliency is the next characteristic in the Reactive manifesto. And resiliency is all about building in these resilient behaviors and characteristics into our application in the case of potential failure at any point in our system. So in this case, if we were to build in built-in resiliency, maybe we'll have built in some sort of feedback mechanism so that our barista can let the coffee shop know that it's stuck because the coffee table's full. In this case, this feedback could then slow down the coffee orders coming to the barista so it doesn't become a potential point of failure or contention or stop the whole application from working. So this behavior is really important to keep our applications up and to keep them responsive. So this all leads to sort of the last characteristic in the Reactive manifesto, which is responsiveness. So being responsive to events and to state changes in our system, whether that's data being sent from an IoT sensor, whether that's clicks on a website, any sort of event to our system that changes, we need to be responding as quickly and efficiently as possible to that so that we can really provide a reactive sort of experience for our end users. So by implementing these 4 characteristics, we can achieve non-blocking, highly responsive, reactive systems from end to end. So I've spoken at a fairly high level of just sort of behaviors and characteristics. How do I go about sort of actually building that when I'm building reactive systems? So we've got an example here of a fairly basic application. It's just got 3 microservices. And then this is just to show you the various different layers and levels that we need to be thinking about to make sure it really is reactive end to end. We've spoken a bit about the data layer and about this importance of sort of making sure that we're decoupling the aspects of our applications by using tools like Kafka, for example, to enable that more event-driven, decoupled sort of data layer. But we also need to be thinking about how our microservices interact with each other. So how the various different components of our architecture interact. And in order to enable the reactive behaviors at this sort of system level, we can utilize something called reactive architecture patterns. So there are lots of different architecture patterns that we could go into. These 4 aren't an extensive list. There are many, many more online. If you just Google reactive architecture design patterns, you'll find lots of resources detailing out each of the patterns that you could utilize in your own application. These are just 4 that we find most commonly used. And in fact, back pressure is one of the most commonly used in reactive systems. And it's one that gets implemented in many of the open source frameworks that we'll go into later. So we've looked at sort of the system level. We're going to zoom in a little bit. We also need to look at within the components themselves, so within the microservices. And within our microservices, we need to make sure that the logic is also asynchronous and non-blocking. And we can do that by implementing something called reactive programming patterns. So what does reactive programming really mean? We've got a basic definition for you here. So reactive programming is really about focusing on this asynchronous programming paradigm, where we're driving forward the logic within our microservices via the availability of new information instead of just by a thread of execution. And you can utilize this by implementing several different patterns, and that's including things like futures, reactive programming libraries, and reactive streams. So if you're familiar with sort of Java programming, as most people I imagine on this conference are, you've probably come across futures before. So futures are essentially a promise to hold the result of some operation until that operation completes. So you can see they're really focusing on that asynchronous style of programming. Then we've got reactive programming libraries. Some examples are RxJava and Small Array Mutiny. In fact, many of the reactive frameworks actually build on top of some of these libraries. And then reactive streams. So reactive streams is really sort of a community-driven specification that's designed to provide a standard for handling these sort of asynchronous data streams while providing the back pressure that I mentioned earlier. So these are some of the techniques that we can utilize and the various different levels that we need to be thinking about in order to make our application reactive. But how do we go about configuring an application that's using Kafka in a very reactive way?
So we've already said that Kafka is a really popular tool to use. And part of the reason for that is that it is very configurable. The community around Kafka is always innovating and there is always new features being added. But when you're standing up a Kafka, because it's so configurable, it means you do have to think a little bit about how it works and how you're going to configure it for your specific use case. So let's look at Kafka with the Reactive Manifesto and the specific configuration options and the underlying pieces in Kafka that you need to understand to get the best out of it in these reactive systems. So let's start with resiliency. So the good news here is that Kafka is designed to be resilient. It has resiliency built into it. It uses a cluster system. So when you stand up Kafka, you stand it up as a cluster of brokers. So a broker is an individual machine that is running Kafka. If you were running in Kubernetes, these would all be individual pods, perhaps as part of a stateful set. So we have these 3 different brokers that are running Kafka. Normally you would start your cluster with at least 3, and we'll start to see a little bit more why in a minute. But you can start with just 1 if it's sort of a test system, but 3 is the sort of standard starting point. So within Kafka, all of the events and messages are held in something called a topic. So Grace earlier introduced the idea of records. So your record is your message or your event. These are all held inside a specific topic. It's up to you to define which records go into which topic. So for example, in our barista sample, we would have one which has the orders, so that's one topic, and then a separate one for the board. Then within a specific topic, that is also broken down further into partitions. So you can have 1 or more partitions that all together make up a topic. We'll see where the partitions come in a minute. But where Kafka provides resiliency is in replication. So when you create a topic, you get to choose a replication factor. So let's say I have this topic here. If I choose a replication factor of 3, what this will mean is that Kafka will elect a leader broker for that topic and then have 2 followers. All of the records that go into my topic will all be sent directly to the leader. So all of those applications that are producing and consuming will just talk to the leader. But But under the covers, because I've set the replication factor to 3, Kafka will automatically replicate everything to the other brokers. So this is a great feature of Kafka, and as I said, you don't have to do anything, Kafka will do it for you. But where this helps for resiliency is that if for some reason one of your brokers were to go down, so let's say for now it's the leader, we haven't lost any data at this point because all of the records on your topic have already been replicated, so we haven't lost anything. And Kafka will automatically kick off a leader election. So it will elect a new leader for that specific topic, and all of the applications that were connected to the first broker will get automatically rerouted to the second broker. So all of the Kafka clients have built in this idea of understanding whether they should be talking to the leader and what happens when one of the leaders goes down. So this is where we have resiliency built in the Kafka brokers. This means you're not going to lose data as long as you have enabled replication for your topic. But how do you make sure that actually you have a resilient flow right from the beginning all the way to the end? So let's first look at producers. A producing application is an application that sends messages or records into Kafka. And there's a few different things you need to consider when you're writing a producer. The first one is to understand what sort of delivery guarantee are you looking for. So you can look at most once delivery or at least once. Kafka does provide some exactly once capabilities, but it's designed for very specific use cases. But in general, you need to basically consider, are you happy to have duplicates in your Kafka topic, or do you not mind actually missing a few of the records going through? Once you've worked that out, then you can decide how to configure your ACKs and your retries. So ACKs is short for acknowledgements, and it's a setting that you set on your producer. If you set ACKs to 0, that's a sort of fire and forget. It'll just send the messages into Kafka and not worry too much about when they got there. This is the quickest, it provides great throughput, but it does mean you can miss records. You can also set ACKs to 1, and this will mean that the leader will basically acknowledge to you that it's received your record. Then the final option is ACKs all. If you set ACKs to all, then your producing application will get an acknowledgement when all of the replication has happened. So this is the most resilient way to do it, because when you produce, you then know that even if the leader broker goes down, that your record has already been replicated. On top of that, you do need to look at doing retries. So most clients do retries by default, but you do need to think about how often do you want to retry, and depending on how many records you're sending at the same time, you might need to consider how that will affect ordering. So we have a few different configuration options here that allow us to make sure that our producers actually get those records they're trying to send into Kafka successfully. So let's look at consumers next. Now, consuming applications, they make sure that they receive all of the records from Kafka using something called offsets. So this is where the stream history of Kafka comes in. In Kafka, all of the records are ordered and they all get an individual number. So this is for a specific partition within a specific topic. So whenever I'm producing, I always add to the end. So if I was producing new records to this topic, I would add 6, 7, 8, etc. Now, because in Kafka, a consumer can reread a record, that means that if I consume, say, the offset 4, and then I'm starting to process it, but something goes wrong, I can always go back and re-pull and reprocess that message. That's the great thing about the stream history in Kafka. Once a record has been read by a specific consumer, it's not lost, it's still in Kafka. But what this means is you need to configure in your applications how you're going to keep track of where your offset is. Now again here, Kafka provides great configuration options for you. It does something called committing offsets. So basically you can store the offset that you've got up to in Kafka itself. And there's a few different options here. You can choose to either manually commit the offset and you handle when you tell Kafka if you successfully read a record, and that's more resilient because you as an application owner know when you've successfully read something. Or you can do automatic if you're just sort of starting out and you don't mind about missing some records. On top of that, if you don't want to store it in Kafka, you can keep track of the offsets yourself, but in general, most people use the Kafka option. So we've looked at resiliency and understood in the Kafka brokers how we get resiliency there, and also how you can configure your producers and your consumers. But what about elasticity? How do you scale Kafka, and how do you scale up and down your Kafka applications? Well, here again, we have our 3 brokers in Kafka, and this is where the partitions really come in for Kafka. So within a topic, it has multiple partitions, as I said, and it's up to you to configure how many partitions you want. But what Kafka will do is it will aim to spread partitions out across the different brokers. So from a producing side, what this means is you can scale up and you have lots of different producers all producing to the same topic, but they'll spread out across the different partitions. So this means you won't overwhelm one specific broker with all of the records for one topic. There are some configuration options you can use that are around the key that you put as part of your record. That means you can direct specific producers to specific partitions, but for a lot of use cases, you'll find that actually just allowing the producers to round robin is quite good. So we've got the producers, and scaling up producers in Kafka is really easy, and then you can scale them back down. But what about consumers? Well, this is achieved in Kafka using consumer groups. So consumer groups is the mechanism that allows Kafka to have multiple consumers working together without them all reading the same records over and over again. So I said before, we have the stream history, and you can have multiple different consumers all reading the same record. But if you want to have it scaled out to lots of consumers reading from the same topic, it makes sense that they don't read the same records as each other. So let's see how this works. When you stand up your consumer, you get to choose a consumer group. So this is just an ID that you give as part of your configuration of your application. Any consumer that joins the Kafka cluster that has the same ID will be put into the same consumer group. So here we have 2 different consumer groups, consumer group A that has 3 consumers and B with 2 consumers. And I have a topic that has 3 partitions. What Kafka will do is it will make sure that between all of the consumers in a specific group, they will read all of the records. So if it's consumer group A, it's quite easy to guess what might happen. They get 1 partition each. So this means between them, they'll read all the records and they won't have any duplicates. But for consumer group B, we only have 2 consumers, but that's okay because one of the consumers can just read from 2 partitions at once. Now, ordering in Kafka is guaranteed per specific partition. What this means is because we want to maintain ordering when you're reading them back, but also because we don't want the consumers to read the same records as each other, if you add an extra consumer to consumer group A, you'll find it doesn't receive any records. So this is how it's supposed to be, because if you were to do that, there is no partition for it to read from where it wouldn't be overlapping with one of the other consumers in the group. What this means is you can, using consumer groups, scale up the number of consumers and scale them back down again. But you can only scale up to the number of partitions that you have. Adding more partitions is perfectly possible, but it does impact ordering. So it's good to work out how many you need in advance. And it's worth noting that the more partitions you have, the more overhead that adds in terms of if a broker goes down and rebalancing happens and that sort of thing. So it's worth taking a bit of time to consider how many partitions you're going to need and aiming to have the right number from the beginning, but not going too far past that number. So we've looked at the reactive manifesto with Kafka and the fact that it provides resiliency and allows you to elastically scale up your applications and scale them back down again. So how do we actually go about writing an application?
So with the standard Java Kafka sort of specification that you get the standard Kafka consumer and the standard Java Kafka producer. But these aren't necessarily designed with reactive in mind. They have some features you can utilize like pause and resume, but what we'd suggest you have a look into is some of the reactive open source frameworks and toolkits that connect with Kafka. So here are some of the examples. This isn't a comprehensive list. It's not every option that you could possibly look at. These are just some of the ones that we've been sort of hands-on with and tried out. And that includes Alpaca, Microprofile, and Vertex. So they each work in different ways. So with the Apache Kafka connector, this is a specific library within the ACK framework. it works using something called an actor framework. So it doesn't really use microservices as such. It uses a different model, a different paradigm, and it uses something called actors. These actors are built in a hierarchical model. So there are parent actors that control work to child actors, and they send asynchronous messages via mailboxes. Now, if you're not already using the actor model, this can be sort of a paradigm shift to sort of get your head around, and it can take quite a bit of re-architecturing to move from something else, another different type of model. But if you're already using the actor model, then the Apache Kafka connector might be a really interesting framework for you to take a look at. There's also microprofile. So microprofile is a community-driven specification, and actually one of their standalone projects, which hopefully at some point will be sort of integrated into the main microprofile stack, is the reactive messaging specification. This reactive messaging specification enables sort of those reactive behaviors and characteristics in the communication within your application. So how does it work? Well, it works using annotations. So microprofile reactive messaging essentially annotates an application's beans methods with either at incoming or at outgoing. And they're connected up via something called channels. These channels are just opaque strings. So you can see an example at the bottom here where we've managed to connect up method A and method B, for example, using that channel, which we've just happened to name order. There are internal channels and external channels. An external channel in this particular framework is called a connector, and there are many different connectors to many different external messaging brokers, for example, including Apache Kafka. And then we've got Vertex as one of the final options we took a look at. So Vertex is a pretty cool sort of toolkit. It's polyglot, so it's not just used for Java. It can also be used for things like JavaScript, Groovy, Kotlin. It runs on the JVM. It's non-blocking. And it has this interesting sort of distributed event bus, which really allows us to have that event-driven architecture throughout the entire application. And the code is single-threaded, which can help with some of those threading headaches. So actually, Vertex was the framework that we decided to use when we were converting one of our Kafka applications into a reactive Kafka application, which Kate's going to take you through now.
Indeed. So yeah, we have a Vertex-based demo application. The aim of this application when we originally wrote it was just to provide people with a starting point to produce and consume to Kafka, because Kafka comes with some really great CLI tools to allow you to produce and consume. But as soon as you want to write a Java application, it can feel like quite a big hurdle to get to that point. And also to understand the different configuration options and how you might configure it if you're turning on things like security. So we wanted an application that was sort of straightforward to run, could produce and consume to a Kafka, and help you to understand how you configured Kafka how you expected and turn the right security pieces on or whatever. So the mechanism that we have for this is we have a Java application that produces a message to Kafka and then consumes it back again. So it's perhaps not what you would do if you were running a business application, but it is a really good way to just test, can I produce and consume to Kafka? And we also wanted to include a UI as part of this. And that was so that we could show not only like this is the message that's been going in, but also what partition has it gone to, what's the offset, just to give people a little bit better understanding of what's actually happening with their record when they give it to the Kafka client. So for this, we originally wrote it using the standard Kafka clients, but we had a chat. So this is actually how this talk came about. I was chatting to Grace about Reactive and said, actually, I ran into all these problems when I was writing my application. Do you think Reactive would help with this? So this is how we ended up writing this Vertex-based app. All of the code is online, so if you want to go try it out for yourself, it can connect to any Kafka that you like, and you get the nice fancy UI to have a look at your application. But it was actually part of needing this UI that was the reason why we had so many problems with writing the first version of this app. So let's just have a look at a little demo of the UI. So for this application, we wanted to be able to have something where you could come in, you could put in a custom message, start producing to Kafka, and it would start sending records in. Then you could start consuming and see those records coming back out from Kafka. But we also wanted a mechanism where we could actually stop producing, stop consuming, maybe change the message, and then continue producing and consuming again. And because we wanted to have this flow of not just having a constant stream of messages coming through, it meant that we actually had to write a slightly more complex application than we originally intended. And when we wrote it using the standard Kafka clients, we found that handling the life cycle of particularly the consuming side, stopping consuming and then continuing again, was actually quite tricky. But that was something that actually was much easier once we switched to Vertex. So let's have a look at why. This is the standard Kafka Java client, and when you write a consuming application, you do a poll. So you basically say, I'm going to get a whole set of new records that have been produced to Kafka, and then you have to loop over them. So what this meant is, because this piece of code is sort of single-threaded, we had to run this somewhere and then like separately handle the messages coming in from the UI and how we interrupt this flow and pause it and resume it. And we did manage to write an application that worked fine, but it was a little bit tricky to get it sort of set up. And when I started talking to Grace about Reactive, it felt like actually these messages, they're actually WebSocket messages that come from the UI. This feels like the thing that our app should be reacting to, rather than us having to write a lot of complex logic to handle that. But if you write with the Vertex client, it's built using reactive programming. So it fits in with that sort of new information coming in that then causes the downstream effects. So here instead what we have is a Kafka consumer handler. So this basically says whenever you get new records, I want you to call this handler. So this means that we're reacting to each new record as it comes in, rather than calling a poll and then looping ourselves. But because of some of the other features that Vertex provides and the fact they have this event loop, it meant we could pull from the WebSocket, pass it along the event loop, and then give it to the handler. So the way we set everything up from a Vertex side just felt like it fit a lot better with our use case. And the more I've looked at Reactive, the more I found that actually switching to a reactive programming language, Kafka, often fits really well with the sorts of applications you want to write. Now, we don't have time in this presentation to go into all the details of the changes we made to this app when we swapped to Vertex. So if you are interested in reading more, then do check out our blog post. So this talks through the specific changes we made on the consuming side and also the actual flow between the UI and the backend that was really nice once we switched to Vertex.
So hopefully in summary, what we've shown you through this sort of quick whistle-stop tour is that just using a non-reactive application and shoving in a tool like Kafka does not make a truly reactive, asynchronous application. What you need to do is you need to carefully consider some of the Kafka configuration that Kate's talked about so that you can make the most responsive and reactive system possible. But you are not alone. The open source community is on hand to help with all of these wonderful open source frameworks, toolkits, and libraries for you to utilize. If you want to get hands-on with some of these APIs, we have created some interactive labs that are freely available for you to go and take a look at. They're all online, so you don't need any local prerequisites downloaded onto your local machine. And you can access those at the link on this slide here. There are about 7 different modules you can pick and choose from all around reactive technologies. I've also written a short book, which I think Sana's put into the chat already. So if you wanted to check that out, it is free and it's available online. And yeah, it just basically summarizes what reactive systems are, when you'd use them, and why.
And then finally, so the product that I work on is IBM Event Stream. So if you are interested in looking at a system to run Kafka, then Event Streams is a really great choice. And finally, we have a set of links for you to check out. So we've put in some reactive resources here if you're interested in reading more about Reactive, and also some great guides for getting started with Kafka. So if you want to do a quick start that sort of takes 10 minutes on a command line, then the quick start guide for Kafka is really great. But if you want to run something in Kubernetes, then I would highly recommend Strimzy, which is an operator for Kafka, which is based on Kubernetes. And then, of course, we have the links to all of the Kafka reactive libraries that we've shared today. So I think that's all we have time for. Thank you so much for listening. It's been great presenting to you, and we'd love to answer any questions.